Okay, well, thank you for the invitation. I'll be talking about Lie groups and robot imagination, and I'll explain a little bit about both. Most of what I'm going to be talking about is the Lie group SE3, and I'll talk about SE3 invariance, the invariance of this group, as well as the concept of equivariance, which I think many people in this field are familiar with, but it's good to have it's a common starting point. Talk a little bit about how to measure distance in SE3 metrics and the invariance properties of certain metrics. Then talk about diffusion processes on SE3. But SE3 is not the end-all be-all. So I'll explain an alternative to SE3 called the pose-change group, something that we worked on, and then look at applications in visual foresight, and then finally robot imagination. Most of what I'm going to be talking about is in my books, so if I run out of time, it's easy to find more information in those sources. Okay, so SE3 invariance. So actually, this is a quite old topic. By old, I don't mean just before LLMs, like 2 years ago. I mean like 200 years ago. Okay, that's what I mean by old. SE3 we can think of as the group of rigid body displacements consisting of rotation translation pairs. But SE3 is not just a rotation translation pair. There's also an operation to multiply or concatenate rigid body motions. So the rotation parts multiply, and then the rotation and translations kind of mix together. And that corresponds to, for example, robot arm kinematics and Denevit-Hartenberg and all of that. So the motion G consists of a rotation translation pair. If we say H, then it's the homogeneous matrix description of rigid body displacements. So here's the old part. We can go back to the late 1700s, early 1800s, when people had time, you know, like Newton, to sit under the apple tree and whatnot and think about things. And so the homogeneous matrices that I mentioned, the rotation translation pair, can be viewed geometrically. Every rigid body displacement going from one reference frame to another reference frame can be affected, can be implemented as a translation along a line in space and a rotation around the same line in space. That's called the screw axis. And so the rotation, so even before these guys, Euler decomposed rotations into the axis angle description. So here, theta is the amount of rotation, n is the axis, which can be either described as a unit vector or as a skew-symmetric matrix like this that has the components of the unit vector embedded in it. So the rotation can be decomposed as e to the theta n, and then the translation can be decomposed in this weird way, which corresponds to the screw description of rigid body displacements. So you have n pointing the direction of this line in space. From your world frame, you construct a vector p that hits that line, and then the displacement is a translation and rotation along that line. Now, this ends up being very important when we talk about invariance, because hidden in these equations are the invariance of rigid body displacements. In particular, and by the way, it doesn't matter if you translate along the line first and then rotate, or rotate around the line first and then translate. These things commute, okay? Usually rigid body motions don't commute, but when it comes to translation and rotation along the same line, then they do commute. So this red displacement vector is the same in both pictures, but just one is rotation first and the other is translation first. Okay, so invariance are the things that remain the same under a change of worldview. And a change of worldview can be described as a conjugation or a similarity transformation by this change of reference motion H0. So the original motion H, which depended on n and p and theta and d, if we conjugate it by an arbitrary rigid body motion, the n part and the p part will change, but theta and d remain the same. In other words, the amount that you've rotated or the amount that you've translated along this screw axis doesn't depend by how you look at the screw axis. Okay, so theta and d are the two invariants of rigid body motion. So what is an invariant? An invariant is something that remains the same as you apply some kind of transformation. So for example, in this first equation, if x is a vector in three-dimensional space and if g is a rotation, then if f is, let's say, the norm of x, then the norm of x is not affected by rotation. So, the function f of x equals the norm of x is invariant under rotation. Equivariance is a looser concept than invariance. So as a completely separate example, let's say x is an image and a color image, and let's say f of x is the grayscale version of the color image. Well, if you first rotate the color image and then turn it to grayscale, or if you turn it to grayscale and then you rotate it, you end up with the same result. And that's what that's an example of equivariance. So the motion doesn't disappear, okay, but it commutes with, let's say, going from color to grayscale. So it comes outside of the function. Okay. And so, well, invariance, for example, can be used in many, many applications. One is sensor calibration, which we did a lot of work on. So the AX equals XB problem, where A and B are known homogeneous transformations measured from sensors, and you want to find an unknown X. And because motions don't commute, you can't just cross off the X. But in order to solve that first equation, because that's the same as A equals XB X inverse, a conjugation, the A and the B have to have the same theta and D in order to be able to solve the problem. Otherwise, it doesn't make sense. And we use that as a filter when you don't have time-stamped data between the A's and B's, for example, in this first paper. And then in these others, X, Y, and Z are unknown, and A, B, C are known, and we want to find the unknowns. So invariance can be used, for example, in sensor calibration. In terms of metrics, how to measure distance in SE3, there's a number of ways to do it, but the basic concept of a metric in mathematics is that it's a function that takes two elements of your space and returns a positive number or non-negative number, and it should be symmetrical. The distance from A to B should be the same as B to A, and the triangle inequality. If you take a detour, then the distance should be longer than if you go directly. And we can add in invariance. We want the invariant metrics. So I'll do my little thing here. So if you have two reference frames and you want to find the different distance between the two reference frames, if you move both of them by the same amount, the distance shouldn't change between reference frames. Okay. So here's a metric that we came up with many, many years ago. I have a little demo here. So you have two rigid bodies, like these two phones, okay? If they're exactly on top of each other, the distance should be 0. If you move them apart, the distance should be bigger. The difference between this kind of distance and regular vector distance is that the centers might have the same distance, but if this rotates relative to here, the distance between the two should change. So the distance between reference frames depends both on the rotation and the translation, and we can induce a distance on the group of rigid body displacements using Euclidean distance. So if you have a point in the body here and the same point in the body here, you measure the distance between those corresponding points, integrate them all up over the body, and that gives you a measure of distance between the bodies, okay? The problem is that there's a square root when you take distance, and if you put that under the integral, it's not in closed form. But if you take that square root outside of the integral, the triangle inequality still holds, but what's inside of the integral can now be computed in closed form. And that closed form integral has a very nice meaning. The rotation part is essentially weighted by the moment of inertia, and the translation is weighted by the mass of the object. Okay, and so that it's a very intuitive way to measure distance between rigid body displacements. And this is invariant. It's left invariant. If we shift the whole scene by g, we shift these two together, the value of distance remains the same. And what's more, if the body is spherical, it's also right invariant under rotations. So if you have G1 and G2, it each is 6 degrees of freedom. Together you have 12 degrees of freedom. We have 6 degrees of invariance by left shift, 3 degrees of invariance due to the rotation of the right shift. So that's 9 out of 12 degrees of freedom. But actually we get 11 out of 12 degrees of freedom because of these theta and d invariants, which are invariant under conjugation. So I wrote a paper some years ago talking about this partial by invariance. 11 out of 12 degrees of freedom invariance. All on the left, 6 degrees of freedom on the left and 5 on the right. Okay, so that's SE3, but SE3, and I've written books, SE3, there have been a lot of papers, did Fourier analysis of functions on SE3. I like SE3, but it's not the end-all be-all, okay? There are other ways of doing things. In particular, on the right is the top part of the right picture is what we all know, right? You have frame, let's say, A, B, C, and to move from A to B, and then B to C, you concatenate homogeneous transformations. What they don't talk about in the intro robotics books, HAB, yes, it's from A to B, but it's seen in A. So you really need 3 subscripts. This is H from A to B as seen in A. H from B to C is seen in B. But oftentimes, in the problems that we're interested in these days in the field, you have a third frame, a camera frame. Let's call that frame O. And you're observing the motion from A to B from O. You're not observing the motion from A to B from A, okay? And so if you want to move everything to frame O, that's a conjugation again, like the first slide that I had. And something really weird happens in that if you conjugate, then what we're really interested in, what is the translation from, let's say, from here to here, from A to B, as seen in O. That's TOAB. But what you get when you conjugate homogeneous transformation matrices is this thing down at the bottom here, which has the TAOB in it, the thing we want, but it has this other stuff in there also, which is very counterintuitive. So what the concept of the pose change group is simply look at translations from your world frame and look at rotations the way we normally do. And when you do that, then the translations just add because they're all in the world frame, the O frame. So you just add vectors because they're in the same reference frame. So this idea of the mixing of the rotation and the translation, we don't need to actually do that if you're observing from the world frame. And so you get basically a direct product instead of a semi-direct product when we do this. The rotations multiply as they usually do, although in opposite order for reasons I won't go into. And then the translations just add, okay? So half the papers I see when people are talking about SE3, they're really doing SO3 separately from translations anyway. So they're really using the pose change group, they just don't know it. And one little tiny thing, one advantage of the pose change group rather than SE3 is if you want to interpolate motions. If you have 2 elements of SE3 and you want to generate some trajectory connecting them, normally we take the log of motion 1 inverse motion 2, multiply by t and exponentiate and let t go from 0 to 1, and you get a motion from the first to the last. The problem is that motion is a corkscrew motion. It's a helical motion. So if you have very large distances and differences in orientation, you get this indirect path. whereas in the post-change group, the translations just go along lines, linearly interpolated. Okay, so I started my career looking at snake-like robots, and we call them hyper-redundant robots, whether they're multi-link robots or continuum robots, anything that's sort of snake-like, elephant trunk-like. With many, many degrees of freedom, we called snake-like robots, what we call hyper-redundant robots. And then my first PhD student back in the 1990s, Emma Ebert-Uphoff, came up with this idea. Well, if we want to characterize the workspace of these kinds of robots, what if we sample the joints and then plot where the hand can reach? Okay, we call that the workspace density. These days it's called reachability, but we called it workspace density way back then. And the immediate problem that we came up with was then if you sample each joint at n, let's say at k states for each joint, and you have n joints, then you have k to the n power samples. So it's you have this exponential problem. But the solution we came up with was we could divide the manipulator into segments, enumerate the states for each segment, and then somehow concatenate those together. And the magic sauce there was that we came up with the idea that if each segment has a probability density and you stack them, then you get the whole workspace density as a convolution on this group of rigid body displacements. And so then, as an engineer thinking of convolution, the next natural question is, was there a Fourier transform concept that could be used? And in fact, there was. In the literature. And so we turned that into a computational tool. And then with my postdoc, Alexander Kiatkin, we wrote a book on various applications of this tool. But this title, non-commutative harmonic analysis, scared a lot of people off. So then we rewrote as a Dover edition more recently. That and the price scared a lot of people off. The CRC books can be $200. So we went Dover, very inexpensive and friendlier title, Harmonic Analysis for Engineers and Applied Scientists. So then from snake robots, we looked at DNA statistical mechanics. You have an elastic DNA filament subjected to Brownian motion. You get all these different configurations. Same math, same workspace density, reachability, et cetera. And then we came to mobile robots, where you no longer have the arc length of the filament of the snake robot, but you have time along a stochastic path. And so here, this is a kinematic part, a wheelchair-like robot with two independently steerable wheels, where there's noise on top, and then this spreads out and gives you, the prior to your mobile robot problems in SLAM that everybody's familiar with. And in fact, we wrote a paper more than 20 years ago on this. Another branding thing we called workspace density. Other people more recently call it reachability. This we called the crescent distribution back then. We should have called it the banana distribution, and then we would have had many, many more citations. The SLAM people would not have ignored us. So whenever you have a stochastic, so this is a stochastic differential equation on SE2, motion group of the plane. And whenever you have a stochastic differential equation, there's a corresponding Fokker-Planck equation. Or if you're Russian, you call it the Kolmogorov equation. And so we can, you can get this partial differential equation describing the evolution of probability density as opposed to an ensemble of sample paths. But then we realized that, well, wait a minute, this is in coordinates x, y, theta. If we think of G rigid body displacements and twists and use all this great Murray Lee and Sastry book, and now the Frank Park and Kevin Lynch book terminology, then we can write this actually without any coordinates, okay? And so this is actually a stochastic differential equation evolving on the group SE2 without any coordinates. So this one at the bottom is the coordinate-free version of this one at the top. And then the Fokker-Planck equation, which we wrote in coordinates, can also be written without coordinates. So just like in Euclidean space, where we can talk about directional derivatives, we can talk about directional derivatives in a Lie group. So here G is the group. You think of it as, well, SE2 in this case. So, and then there are infinitesimal motions. This X1, X2, X3 correspond to infinitesimal translation in the X and Y direction and rotation around the Z direction. So we can ask if you have a function on SE2 and you want to take its derivative, for example, if you want to do gradient descent, you can do that without coordinates. You can just perturb the function a little bit in the direction and evaluate, okay? So basically you could this equation at the top, you can evaluate by finite difference. And we've done that in a number of papers in a number of areas. And the Fokker-Planck equation then that looked very messy in coordinates it just looks like a homogeneous diffusion now because all of the messiness was actually because the derivatives were expressed in coordinates when they could be expressed coordinate free. And then we wrote this paper 12 years ago at RSS saying the banana distribution. See, we were 10 years late, but we catch up. And so we said the banana distribution is Gaussian. And we said, well, what do you mean the banana distribution? How can it be Gaussian? It looks like a banana. It doesn't have elliptical level curves. Well, the banana distribution is Gaussian in the exponential coordinates of this Lie group, not in x, y, theta coordinates. So if you use the right coordinates, you can call it a Gaussian. So that's what that paper was about. And so all of this math can be summarized here. We can do convolution on groups. So everyone loves convolutional neural networks. Instead of just doing it in translation, you can do convolution on groups. You can do Fourier analysis on groups. You can do probability and statistics on groups. So there's a concept of mean, a concept of covariance, and these concepts under convolution transform in nice ways. These are actually approximate equations, which there are higher order corrections to, but these work quite well for concentrated distributions. And again, so that's what these first two books are about: stochastic models, information theory, and Lie groups, because everything I've been talking about are stochastic models on Lie groups. And the information theory part comes in, for example, various inequalities related to convolution and entropy and things like that that you find in information theory. Okay, so now we'll talk about a little bit about the fun stuff and some recent work. My students are here, so they can tell you more detail if I miss some things. So this is a paper that came out in TRO very recently. It's probabilistically informed motion primitives for affordance learning from demonstration. So this is a learning from demonstration method. And here again, there's no snake robots, but there are trajectories. Okay, so you have demonstration trajectories. The one on the left, former research fellow Sipu was scooping. He's scooping little crumpled pieces of paper from a particular bowl. And then on the right, that scooping demonstration is generalized to scooping other materials like cereal out of other bowls and in the presence of obstacles that were not there during the training. Okay, so that's what PRIMP does, is it generalizes the initial training, and the approach uses SE3 Gaussian distributions. And the idea is that you have an ensemble of trained trajectories. K denotes the kth demonstration. And each one of these is on a normalized time scale, let's say from 0 to 1, and then we divide up the trajectory into n segments. And then going from the beginning of segment I to the end of segment I, so we collect all of those reference frames from the set of demonstrations. So we get a little cloud of reference frames, just like workspace density. And so this transitional probability here we describe by a mean and a covariance on the group SE3. And then for the whole trajectory, the whole set of demonstrations, we generate a big Gaussian distribution on SE3 to the n power, so n copies of SE3. And then we can sample from that big distribution and get candidate trajectories. And we can weed out those candidate trajectories based on whether they, well, first of all, we have a cost function that we want to minimize. We want to stay as close to the mean of the demonstrations as possible, but we don't want to hit obstacles either. So we can throw away trajectories that, that hit obstacles, and whilst trying to push towards the demonstration performance. And so here's some examples of that. We've done it on opening doors and drawers, pouring and scooping, things like that. So it's pretty agnostic because it doesn't depend on the robot. It depends on where the end effector was going. Okay, all the robot stuff, the collision and everything else can be done after. I mean, when we weed out trajectories. Another piece of work that we did was on visual foresight. And here you'll see an example of how equivariance comes in. So here the idea is that O sub t is our observation, like it's an overhead camera image of a scene. Then we have an action, like pick up from here and move over to here. And then they trained the visual foresight model to encode the relationship between what will the image look like after a pick and place procedure. And, you know, but we could have moved the whole scene and the action, displaced the action first. And the idea is that this model has built into it equivariance. So in other words, so why do that? Well, equivariance gives you some data efficiency. You train, you know, picking and placing over here, but then you can shift everything and it will work equally well. So you sort of mod out the irrelevant motions that have no effect on the actions that have been learned. So Jikai sitting in the middle there is one of the authors who can tell you much more about this than I can, because I don't do any coding. I just have conversations with people. That's all I do. Okay, and I don't even with ChatGPT. I don't even correct English anymore. I just have conversations. So and so the visual foresight was applied here to tower building, given a heat map of the height of a tower you want to build, and given some blocks randomly set out on the plane. This built towers. Okay, with previously untrained. I mean, there was no go here and pick that. It's just here's the blocks, build a tower, and here's the height map for the tower. And so this worked quite well. But the thing that we're doing in my lab now that I'm most enthusiastic about is what I call robot imagination. So I know learning is very popular these days in robotics, but there's this quote by Einstein that imagination is more important than knowledge. And learning is about acquiring knowledge. So imagination goes beyond learning, okay? So the idea is, how can we develop truly smart robots that can assess the affordances of previously unseen objects? So if some, I have papers like, harmonic analysis on, semi-direct product groups, et cetera. But more recently, we have papers like, is that a chair? Or can I pour into it, et cetera. So the concept is this: the robot comes to this object, it's never seen the object before, and it asks the question, is that a chair? Well, the way at least the way I would reason if it's a chair is there a way to turn it so that I can sit on it? Okay. So the essential feature of a chair is not whether it has 4 legs or whatever. Is it so-called sittable? So we've invented that word, sittable. Okay. So is the chair, can you sit on the chair? And so we do that in physics-based simulation. And so if the robot can imagine that there's a humanoid figure that can somehow sit on the chair, if there's some orientation of the chair that will support sitting, then the robot determines it's a chair, okay, because it can be used as a chair. And so this was a recent RAL paper that we published. And Meng Xin is sitting over here. Easy to find her because she has pink hair. So prepare the chair for the bear was this paper. So here's how it goes. As I say, the chair geometries don't matter. But what does matter is there a way to orient it so that it can be used as a chair? The chair could be upside down, it could be against a wall. And so how can a robot that encounters this object determine what it can be used for? So we're actually building out a dictionary of affordances of objects. Chair is just one of them. So what could it possibly be used for? Is it sittable? How does it need to be oriented, etc. In fact, you need to solve the orientation problem before assessing. So here's the scenario. So this Franca is doing a 3D scan of the object, getting a point cloud. Then, so it has a partial point cloud. There are April tags attached to the chair. So it doesn't know what it is, but it does know where it can grasp it. Then anyway, it has the partial point cloud, throws that into Isaac-Jim and plays with it to see where are the stable ways that this can land. Then it turns it over and sets the chair on one of those stable orientations so that it can scan the other side. Okay. And then after it scans the other side, it's going to put the whole thing in a simulation to see, dropping simulation to see how the chair can be oriented. I don't know why this is going so slow, but I think we can skip it. Oh, it's going slow because it was being careful not to collide with the table. Anyway, that's not the main point. Okay, then it's scanned. I think I skipped 2 slides here. Okay, then well, anyway, then it scans it. It puts it in the physics-based simulation, figures out where it can be placed. Okay, here it's scanning the top. Then it's going to put it in the physics-based simulation. Then it's going to drop humanoid figures on it, see what will support sitting. So here it's seeing how the different stable orientations first, then supporting sitting. Okay, and then after it determines what the best orientation for a humanoid to sit on the figure, on the chair is, then that's when it goes back to the real world and goes back to the real world and then moves the chair over to the now. And the now's job is to put the bear on the chair. Now, that was another paper we wrote. So this was prepare the chair for the bear. The first one was put the bear on the chair. So then it moves it over. So now it completely knows the model, knows how a humanoid can, figure can sit on the chair, moves it over to the now. And then the now's job is to put the bear on the chair. Okay, so it's tracking. And then Mengxin gives the bear to the now, and then the now puts the bear on the chair. Okay, which I guess is the next video. Let's see. Yeah. Okay. So it looks like an easy task, but the bear is a passive multi-degree of freedom thing. The humanoid is multi-degree of freedom. If it puts it in the wrong place, it'll fall off the chair. But anyway, so the key here was that this object was previously unseen. The robot determined, the system determined that there was an orientation of the chair that supported sitting. It moved the chair over so that we could demonstrate the sittability of the chair with the bear. Okay. Now, where's the geometry, equivariance, et cetera, in all of this? Well, in the evaluation of the orientations of the chair that are sittable, there's a don't care condition about translation in the plane and rotation in the plane, so we can divide that out. Okay, so that's actually the concept of a quotient space, or in this case, a coset space of SE3 quotiented by SE2. So there's some math behind there, but you know, we put cute pictures of teddy bears on chairs, and everyone likes that more than the math. So and just go with the flow. Anyway, I'll conclude now. I think I have a couple minutes for questions even. But all the math is in the books and papers, and I'm happy to talk to folks about that. So I'll open up for questions. Oh, there's.
So with affordances, what is afforded to your system is coupled with what your robot looks like, or the thing that the agent that's observing the structure.
Mhm.
How are you decoupling or coupling that together? Because a robot could be looking at something that is a chair, and it looks like a chair, but it might be too big to actually be able to sit in the chair, so it's no longer afforded to that system.
Yeah, so that all comes out in the simulation. Maybe, I don't know if everyone could hear that online. So the question is, how do you decouple the robot's properties from the affordances of the object? And our approach is that because it's all physics-based simulation of the object, like dropping the humanoid figure on the chair had nothing to do with the robot and how it was doing things, right? And the bare size relative to the chair size that would come out in simulation and before the robot touches anything. Now, another question is the robot able to put the bear on the chair? That's a different question than answering the affordance of the chair. So we answer the affordance completely decoupled.
Thank you for the great talk. And you said we use maps of the object in the matrix, so you have to make certain assumptions about the physical properties of the object rather than just the geometry. And I'm wondering, basically, if you assume different masses for the objects, how does that translate exactly to the metric? Does it scale proportionally, or is it?
Yeah, I'll try to repeat your question. The question is with regard to the metrics that I mentioned, is the choice of mass distribution, for example, moment of inertia and mass, how does that affect the metric properties? So the answer is, so the reason why we're using that, so and we just like are assuming a uniform mass over the objects, simply because rotations have units, radians or degrees, and translations have other units, millimeters or inches or whatever. And you can't just take those two quantities and add them together and get a meaningful result. But if you weight the rotations by something which has units of moment of inertia, and you weight translations by something that has units of mass, then everything has the same units. So if we made the total density 10 times more, the metric value would be 10 times more, but it's a relative measurement anyway. And we're only doing this so that the rotations and translations have the same units, not to, so we basically, you could put a probability density instead of a mass density on the object, and it doesn't have to be uniform, but we're using uniform on objects to give a sense, so that if you have something that's a concentrated little sphere, or something that's very long, like a pool stick or a ladder or something, then when you measure distance, that the shape should be of the object that's being moved should be reflected in the metric itself, because it's that object which is being moved from A to B.
Yeah, that makes a lot of sense. Like the unification of the metrics, pretty different units. That makes sense to me. I was just wondering if actually these real objects that have different masses still assume a uniform distribution. Although they have the same shape, what happens to the metric?
Yeah, it would change. If you had a styrofoam box with a little ingot of uranium, then yes, then it would be different. But that's more like a dynamics or a mechanics thing. This was more for a kinematic kind of sense.
Yeah. Okay. And the other question was about the distribution over the demonstration, where you now we have to know about the problem with that distribution that was the Gaussian, but you had the basically the normal distribution.
Yes.
And I was wondering, there's like let's say, for example, bring these multimodal solutions from a multimodal demonstration. And I'm wondering how you think about that with your framework. There is a way to change it so that it could also capture multimodality.
Right, so currently it's unimodal. I mean, you could do something like a kernel trick and bump up the dimension, and then you have just a big Gaussian, but then, you know, yes, I guess if you could go this way, or you could go that way, or there's, tying a tie or shoelaces, there's very different strategies, if you do double knot, or there's different, so that would be a multimodal thing, but this was really unimodal. Yeah.
Very nice. So I was wondering about the definition of the Brownian motion. When you're talking about the SEs, and for that matter, the definition of the Gaussian of the Lie group. Is it just the Gaussian on the algebra, or is it something more sophisticated?
Yes. Okay, so let me repeat the question so folks can hear. So the question is the Gaussian on the Lie group just the Gaussian on the Lie algebra? And the answer is yes, here it is, but shifted. I mean, there can be a mean, so you wouldn't just take the mean, shift to the Lie algebra, and then do a Gaussian there. We shift the whole problem so the mean is at the identity, and do the Lie algebra from there. Now, if the covariance is small, that's all fine. The covariance gets bigger, you have to do weird things like wrapping the Gaussian around the group. And if the covariance gets really big, then the concept of mean and covariance break down. Then you have to use Fourier analysis on the group, which is my other book.
Oh, so it's if you have a large covariance, you have to define it through the.
Well, just think on the circle. If you have heat diffusion on the circle, in the infinite limit, it becomes the uniform distribution on the circle. A Gaussian is not a good approach there, but a Fourier series is, because the first coefficient in the Fourier series is the constant number 1. So there's extremes, and as things become very diffuse, Fourier analysis is the tool. If things are more concentrated, then a Gaussian is more appropriate.
This would be related in a way to the concept of concentrated Gaussian-like distributions on the manifolds, like Bingham, normalizes, all that stuff.
That's another approach other than Fourier, but yes, that handles things that are more distributed.
The metric, the distance metric that you propose, what's the purpose of that versus something else? Is it just that you can give it in closed form, unlike a running distance?
It's in closed form, it has uniform units, and it's intuitive. Yeah.
And then you said you weren't going to answer this one, but why are the rotations multiplied backwards in this question?
It has to do with conjugation, and are you in the world frame or the body fixed frame? If you do rotations in the world frame, that you do them in the opposite direction. We're used to doing incremental rotations in the body frame. I think I'm being kicked out.
No.
Okay.
I think you can take maybe one more question.
One more. Okay.
Yeah, another question about the metric. I was wondering what part of the things that you described afterwards rely on having that metric. For example, the Fourier transform you mentioned. Does that require the metric to be that?
No, so what's the metric I mentioned, I said it's partially bi-invariant. So SE3 does not admit a fully bi-invariant metric, but SE3 does admit a fully bi-invariant integration measure. The volume element is just dr times dt. And because of that's what's called a unimodular Lie group, if it has that property. And so SE3 is unimodular, and so you can do lots of nice Fourier analysis on SE3. And the fact that the metric, that no bi-invariant metric exists, doesn't hamper you from doing Fourier analysis on that group.
Thanks.
Thank you for a great talk. I was wondering whether you can comment more about SE3 group or post-change group, especially for the optimization of the base.
Well, as I said, I think half the people who think they're using SE3 are using the direct product anyway. And in our print paper, we compared both, and actually the direct product worked better in some scenarios than SE3. So I can't tell you when it's better, but what I can tell you is this: if you're doing non-holonomic constraints like a mobile robot, or doing kinematics along a chain with relative motions, then SE3 is the way to go, because it's capturing that local concatenation. But if you're not multiplying homogeneous transformations, if you're not looking at relative motions, then it probably doesn't matter. Just treating it as a rotation translation pair is fine.
Cool.
Okay.
Think,
Well,
Yeah.
well,
You talked about the post change group. I was just wondering, when we do learning, like if we're convolutional neural networks on image spaces, usually they're centered on the object. So it's like you have that symmetry about SO2.
mhm.
There's a lot of problems where that object might be away from center of view, off to the side or onto another plane. I was wondering if this might help us mathematical tools to handle symmetry where objects are not symmetrical.
Yeah, so let me repeat the question. Is there a way to handle the objects and images not toward the center in CNNs, for example? And well, because CNN is basically a Fourier series of the image, those are translationally invariant, right? You can shift, but you can also use the FFT to rotate, right, by doing 3 consecutive shears, and there's various classical methods for doing that. So I think it should be okay. Now, whether it's exactly mathematically equivariant or not, but functionally, if you're down to machine precision, you're doing okay, then I think things should be okay, which is probably why folks don't use the stuff from my books. They use the classical FFT stuff in learning because it works well enough, I think.
cool.
Okay.
Yeah, I think that's.
Okay, thank you.
Yeah.
Okay.